Okay, let us wait for a few minutes, then we can start. Okay.
Beg pardon.
What?
Can you repeat what you said?
Your voice is breaking. Can you repeat it?
Okay. Actually, I was my microphone was not working at that time.
Okay, okay, okay. No problem. Okay. No, I was just saying that wait for a few minutes, then we can start. Okay. After
Okay.
one or
Okay.
two
Fine.
minutes. Okay.
Fine.
Okay. Is there any doubt from assignment questions or previous lectures uploaded in that week? Okay. So then let me start sharing my screen. Okay. Let me just connect this. Now is this visible?
Yes. Yes.
Okay. Okay. So today I planned that first I will discuss very little about electronic partition function, though it's discussed in class. But I thought that because there are some parts remaining, so I have discussed that electronic partition function, then Gibbs paradox, which is very important uh, in in statistical thermodynamics, because it's actually due to the Gibbs paradox, as name suggests, it's a paradox. It's given by proposed by Gibbs, and due to this Gibbs paradox, that idea of that n factorial, those we added like q to the power n by n factorial, that appears, so that we can understand with the example. So that's why I will discuss the Gibbs paradox. Then I thought to discuss about grand canonical ensemble. Okay, to derive the grand canonical partition function. That is important because we know that after deriving partition function for any ensemble from partition function, we can derive any thermodynamic quantity, right? Internal energy, enthalpy, entropy, as we have already derived for canonical partition function. So the similar treatment can be done once we obtain the partition function for the grand canonical ensemble. So that we'll discuss today. And I also I'll go through some questions from the assignment. I was looking on the assignment question, so from 5, 6, and 7 or 8 as well. So that's today's plan. So let us start. Or if you have any other doubt, any question, you can ask me. Okay. So electronic partition function. If in terms of question, if you like to derive electronic partition function, I'm just writing electronic partition function. Okay. So we know the general definition for any partition function, which actually is just sum over j gj e to the power minus beta epsilon j. So this is the definition for the partition function. That may be electronic, that may be rotational, vibrational. That does not matter. Um, Molecular partition function. This is molecular partition function, obviously. Molecular partition function. Now it may be anything. The definition is general. So as we have already discussed that translational or the rotational or the vibrational, here also we have to find out first the energy levels for the electronic partition function, because here we have this epsilon j or epsilon ej terms. That means the energy levels that is needed. Okay, so from where we can have any idea about an electronic energy level. Electronic energy level means, do you understand? What does it mean? That means while rotating around the nucleus, that energy levels in which that electrons can revolve around the nucleus, that is called the electronic energy levels. Okay, so do you have any idea from where we can get the energy values of the eigenstates? Am I clear? Yes.
Are you pointing towards solving Schrodinger equation?
No. uh, we need just like think about vibrational. If you consider vibrational partition function, the vibrational energy levels from where we have derived that simple harmony oscillator, right?
Yes.
The energy levels from simple harmony oscillator. If you consider the rotational partition function, from where we have derived that energy levels from rigid rotor model. That if you solve the rigid rotor model, you will have that energy levels. For that, in translational partition function, we know we derive from the 1D box, particle in a box. So for electronic energy levels, which model should we consider? That I am asking. Just we have to extract the energy levels from that model. That we have already done. Everybody has done. That is hydrogen atom model, right?
Yes.
While solving hydrogen atom, what we have obtained ultimately the energy levels, right? 1s, 2s, 3s, that energy levels, energy values. These we have already obtained, the quantum number. These things already we have obtained. So that we needed the energy levels we needed here. So it's clear. So what is the energy for hydrogen atom? For electrons revolving in hydrogen atom, not hydrogen atom. So it was En was minus 2 pi square
2 pi
m
n
z square e to the
to the
power
power
4 divided by
n square h square.
n square. So that's I was asking. That is already we have studied in 11, 12 level. So this is the energy for the electrons while revolving the hydrogen. Why I am taking the hydrogen atom model? Because that is only solvable model we have. Apart from hydrogen atom model, there is no other model which can be solved exactly without any approximation. There is no any other model. So everything, the orbit shape of orbital, the electron distribution, everything we have studied, the energy of electron, that is everything is regarding the hydrogen atom model only, because that is totally solvable model. So here you can see this energy is only En. En means only we are considering the principal quantum number. That means the or orbit. Orbit. You know that in orbit there is also L. That means the suborbit. Then also the M, the orbital. This we are not considering, because you know these are very narrowly spaced. So we can just like you can think, if this is n equals to 1, then under this you will have What will be the L? You know, this N,
0 and 1.
yes, N is 1, 2, 3 to up to infinity. It can go in principle. L is 0 to n minus 1, and M is minus L to plus L.
Plus
These three quantum numbers are there, right? So, is there any other quantum number?
P.
Pin quantum number.
Yes. What is that? S, right?
A is equal to half.
Or minus half. 1 minute. Let me grab my Bluetooth again. Disconnect. I do. Few days it's happening. Bluetooth is getting disconnected. So, let me disconnect from the. Do you have solved the hydrogen atom problem in BSc level? It is also solved. It's studied. Hydrogen atom problem. Do you have
Yes.
studied? Okay. So from Schrodinger equation, when you solve this this Schrodinger equation, while solving Schrodinger equation, you obtain the energy value. So what quantum numbers have you obtained while solving this? Do you
What
remember?
quantum number means?
Means among these four quantum numbers, N, L, M, S, all you have obtained derived solving this hydrogen atom.
NLM 3.
NLM, exactly. S you did not obtain. If you remember clearly, because this quantum number obtained while solving Schrodinger equation only. If you consider the hydrogen 1D box, while solving 1D box, you obtain this n, right? This f e n equals to n square h square by 8 ml square. This you obtain while solving the 1D box. While solving the rigid rotor, you obtain the 2j, the quantum number j, 2j plus 1 into that 2bj into j plus 1. What is the formula? That is this quantum number only you can obtain for high, if you remember, for the vibrational or simple harmonic oscillator, the quantum number is um, h nu, n plus nu plus half
N plus half h.
n on nu. You can both. This is v actually, not d, v. V for vibrational. That's why v. V plus half h nu. This is also when you solve the quantum Schrodinger equation, you will obtain this quantum number. Okay, that's why these are called quantum states, eigenstates. Okay, but when you solve the hydrogen atom, the Schrodinger equation for hydrogen atom, you will only have this n, l, and m. Okay, these three quantum number you will obtain. S you did not, never you can't get this S quantum number. So eventually, while solving the hydrogen atom, you will get N, L, and M. Very later, while during an experiment with, I think, Oram or AG silver, I don't remember, but during an experiment, it was observed that there must be another quantum number, which essentially again split the energy level into factor. So, but that was not theoretically proved. After that, do you know why this S is not obtained? Now you know there is a quantum number S that essentially signifies the spin of the electron. But while solving the Schrodinger equation, you will not get this. So S is not only a quantum phenomena. There is another thing to obtain S, because while considering the quantum states, you can have N, L, and M. If you solve H cross del psi del T equals to H psi, if you solve it, you will obtain this three only. S you can't for hydrogen atom. Can you guess when you can have this S theoretically? What factor should you include? As you have already studied the hydrogen atom problem, that's why I'm asking. One factor you did not consider while solving the hydrogen atom. Just guess it. What it can be. Okay. So For that, we have to consider the relativistic quantum mechanics. Okay, that because it's electron, and you know the speed of the electron is essentially c by 137. So that is not very less. That is not very. You can't ignore the relativistic effect at that speed. So you have to consider the relativistic Schrodinger equation. This is no normal Schrodinger equation. Okay, this is not relativistic Schrodinger equation. If you consider the relativistic Schrodinger equation, which is actually Dirac equation, Dirac did this. So while solving the Dirac equation, ln m will you will obtain, also you will obtain the s, that is plus half and minus half. So that is totally, speed is totally quantum phenomena, obviously, but not only quantum phenomena. This is also relativistic quantum phenomena. If you consider the relativity, then only you will have spin. Otherwise, let's say electron is rotating, revolving around nucleus. Electron has spin, but that is only possible when spin is quanta is only possible when the electron has a speed which is comparable to the light. That means you can't ignore the relativistic effect. Comparable means c by 137. That is also high enough to consider the relativistic effect that I want to mean. Okay, so that's now if you solve it, so you know n equals to 1, so L will be just 0 to n minus 1. So it will be 0. So it will be just only L will be 0 and S will be also not M will be also 0. So that is, we know, that's why it is actually 1s. For n equals to 1 is very trivial. So let we consider the n equals to 2. So if you split it, n equals to 2, then L will be 0 and 1. So it is L equals to 0, L equals to 1. Again, from L equals to 0, you will have M equals to 0, and here you will have m equals to minus 1, m equals to 0, m equals to plus 1. So eventually there are 4 levels. Under n equals to 2, there are 4 levels. So here I have drawn just one level, but essentially these are the 4 degenerate levels. Why I'm saying degenerate? Because these energy gaps are very small. Although these levels are not degenerate, but to break that degeneracy, you will need very, very, very precious measurement. Then only you can have. So after, if you consider the suborbit, then L quantum number, then it will be 2 level. Also in one, there is also 3 degenerate level. So it will look like this actually. And you know, to have this M, this is actually the magnetic quantum number. To have that level, splitting this to make this level degenerate in 3 levels, you have to uh, apply a external magnetic field only. Then only it will degenerate. It will be. That's why you remember how we draw. This is 2s and these three are degenerate. That's why we draw as 2p. When you apply a external magnetic field, then it will be break in px, qi, and pz. So that I was saying, here we are not considering this A also. We are considering this 4 level as degenerate. Because while considering the rotation of electron or revolving of electron, this sp, these quantum numbers does not make very difference. So n is the main factor which actually contribute in the energy. Okay, these energy levels are not very well separated. These are close enough, so we can consider the energy only guided by the quantum number n. That's why we only consider that en. Okay, so en is our energy, which is our non primary quantum number. Okay, so if this is true, then let me write it again. The En form of En, it was, why there is a minus sign?
It's a bound state.
It's a bound state. Exactly, because that means while entering electron in that energy level, it will get stabilized. This is nucleus, and if you consider around the electronic states like this, that it is negative means we are considering when it's a free electron, that means it has zero energy. So when electron comes in any energy level, it will come because it will be stabilized because there is a positive charge in the nucleus, and hence it will be stabilized. The energy will be less than zero because when it is free, it has the energy of is zero, so it will be zero negative. That's why it is minus 2 pi square mz square by n square h square. N is a quantum number. Okay, so now we can simplify it. So it is uh, minus these things z square by n square electron volt in terms of if you calculate in terms of electron volt, you will get this. Okay, for hydrogen atom Z is 1, or in terms of centimeter inverse also, you will have minus 1097.7 Z square by n square. This is not that much important because this is in terms of centimeter wave number form, but this is very important. Okay, one thing now. So this is clear. En we have. For partition function, what else we need? Except the energy of the nth state, what else we need to write down the expression of partition function? What is that? Q is Q electronic. It should be now. Let me write n. So it e to the power minus beta en. En we have the expression for en, and we also need the gn, right? The degeneracy. What is the gn?
1.
1. Why?
It has no degeneracy.
It has no degeneracy. Here you can see for n equals to 1, degeneracy is 1, but for n equals to 2, how many degeneracy are there?
4.
Degeneracy 4. How the 4 comes? That's why I discussed these things. Because when you break down it, uh, first you have to break down in terms of L, then in terms of N, then in terms of the S. S I have not done here. So that we have to consider. Okay, so it's 4, but actually we have not considered the spin. So if you consider the spin, then it will be 8. Because when you consider the spin, each state will again degenerate. Yeah, will again split in two parts. Plus up, minus up, plus up, minus up. So how it comes? If you do it, let's say if it is n, for any quantum number n, so L will be 0, 1, 2, n minus 1. For 0, m will be 0. For a1, m will be plus 1, 0, minus 1. For 2, again it will be minus 2, minus 1, 0. This plus 1, 1. For each m, there will be a spin quantum number. So again, it will be up spin, down spin, up spin, down spin. In this way, you can calculate the total degeneracy. So here you can see, so total here it is just n square. N square. If you don't consider the spin, it will be n square. So if you consider the spin, then it will be multiplied by 2. So it will be 2n square. Okay. So you can check. Let's say n equals to 4. So what it should be? Degeneracy should be gn equals to 2n square. So it is 2 into 16. So it should be 32. Let us check. If n equals to 4, then L will be 0, 1, 2, 3. For 0, m will be 0, and that means 2 state we will have. Okay. Here it will be plus 1, 0, minus 1. Up for each state it will be up spin, down spin, again up spin, down spin, up spin, down spin. So we here up spin, down spin. So here we have 2, here we can have 6. Here how many state we have? Plus 2, plus 1, 0, minus 1, minus 2. Again each state will be split into state. If you consider the spin, up spin and down spin. So again, it is 10. If you calculate for 3, it will be 18. So 2, 6, 10, 18. So total is 8,
36.
36, right? So I have
uh,
done
32.
no, no, then I should calculate. So m is plus 3
32.
plus 2, yes, 32. 32, it should be 32. It So it is up spin, down spin, again up spin, down spin. Yes, it will be 12. Hmm. That I have
14.
14. So it is 32, right? Total 14. So 2, 8, 18, 32. So that's why in AS, this essentially, guys, this M is when M is 0, it's actually the S orbital. And in S orbital, there are only 2 electrons can be there. When M is equal to plus 1, 0, minus 1, it's essentially Q. And in P orbital, there can be 6 electron. This is D, 10 electron D10, and this is essentially F. In F, it will be 14. Okay, so total 32 electron will be there. So now we have Gn, En. So we can write down the partition function for the electrons, electronic partition function. So it will be sum over n to n square e to the power minus beta. Now what was the energy? It was minus 13.6 z square by n square. Okay, clear? So this is our partition function. If
But it is the energy of only nth state,
energy of the,
nth orbital.
yes, that's the nth energy level. You have the summation. So what was the definition of partition function? It was the energy level J instead
Summation
of
of all
J.
the energies.
Yes, instead of J, I have written the N. You can write J as well because in electronic state, N is written in general. The convention, the orbits are written in terms of quantum number N. That's why I have written the N. It's just same Gj e to the power minus beta Ej. Instead of Ej, I have write in terms of that N, En. This is the energy of the any nth energy level. Just you have drawn. I'll draw. So what was the energy levels now? Energy levels, we know that En equals to minus 13.6 for Z square by, let's consider the hydrogen atom. So minus 13.6 by n square in terms of electron volt only. So you have to keep in mind that when I am putting this value in terms of electron volt, then obviously beta, that should be also in the electron volt. That you have to keep in mind, okay? Otherwise, it will be wrong because ultimately this should be neutral. This should not have any unit, beta E. So when I have written in terms of, so it's better to write electron volt also. Or if you want to write in terms of joule, then you have to convert it. Then it will be joule, and now you can write down beta. Okay. So now, if you draw the energy levels now, first will be E1. What will be the energy of E1?
Minus 13.6 electron volt.
Yes, these things you have studied, right? Minus 13.6 electron volt. This is actually the E1 or epsilon or whatever you want to write. Then
Minus 3.4 electron volt.
minus 3 points. Just we have to divide by 4. So minus 3.4. So it will be iron. Let me write it here. So it is E2 minus 3.4 electron volt. Then it will be E3. What will be the energy for E3? Just do
Minus 0.51. Sorry, 1.51.
1.51. So now it will get closer. This diagram you have already seen in 11-12 book. It's there. So now it will be minus 13.6 by 16. So it will be 0.85.
It will be getting more closer and closer.
More closer and closer. Like this, it will So these are the energy levels. Okay. So let me write it also. It is minus 0.85 electron volt and goes on E4, E5, so on. Okay. So these we have to add. So if you write, then what will be our partition function? Partition function will be, so when uh, for first state, degeneracy is 2n square means 1. Just I am opening the sum. So it will be 2 by 2. 2n square, n is 1, so it will be 2 e to the power minus beta. Let 13.6, because you can write it. You can see E1 is actually minus 13.6, right? So En can be written as E1 divided by n square. See, we can write it.
Yes.
Yes. So then it can be written E1 by n square. So this is the general form you can write, because here there is no electron volt or joule, because when you have write in terms of the E1, it will be cancelled out. So it will be 2n square e to the power minus beta E1. E1 is the ground state energy by n square. So this is partition function, final form. And here you can write E1 is essentially minus 3.6 electron volt in terms of electron volt. Okay. Or Z square. Z square you can write for hydrogen atom, there is one. Okay. So this is our E. Now if you open it, then you will have 2 e to the power minus beta E1 plus. It will be 8, right? 8 e to the power minus beta E1 by 4. Then it will be 3, it will be 18.
18.
18 e to the power beta E1 by 3, E1 by 9, and so on. So this is how the partition functions. One thing we can do, it will goes up to infinity, essentially, and infinity it is 0. That means it's a free electron, essentially. So it goes up to the infinity. Okay. So one thing for simplicity you can do, but it's not necessary. It's not necessary. You can you have studied that. Only you have to consider the first energy level. After, other energy levels are, so if you consider that also, just listen carefully, because this is very important here also. This is similar to the harmony oscillator part. Yes, it's correct. This part, this E1 by 4, it is getting very, very late, because you can see here it is minus 13.6, it is minus 3.4. So you can ignore. These terms you can definitely ignore. If you consider up to first, second term, it's okay. But in general, what we consider, because this energy gap is very high compared to rotational and or vibrational, these energy gaps in terms of electron volt, so it's very, very high. So it's very high energy gap. Let for idea, just I am calculating. Let me calculate beta. So what will be the beta E1? Beta E1 is beta is 1 by kBT. Let's say in room temperature. Room temperature is 300 Kelvin, you can consider. So in 300 Kelvin, beta epsilon 1 will be, you can calculate it, is minus 13.6 into 1.16 into 10 to the power minus 19. 1 electron volt is 1.16 into 10 to the power minus 19 joule. So it will be multiplied by 1.16 into 10 to the minus 19 joule. Just to do it, so it will be minus 13.6 to 1.16 into 10 to the power minus 19 divided by kb. Kb is 1.38 into 10 to the power minus 23, and T, let's say 300 at room temperature. So if you calculate it, you will have minus about 13.6, 1.16 divided by 1.38 divided by 300. So it is eventually 0.038 into 10 to the power 4. So it is 381 around approximately. So minus beta h1 will be, so minus, so now if you write it, so QE will be 2 into e to the power 381 plus 8 into e to the power 381 divided by 4 plus 18 into e to the power 381 divided by 9 and so on. So first term e to the, so now you can see it is just beta e1, it now, it's now dimensionless because we have considered kb, 1.38 into the minus 23, so it's also in terms of joule. Okay, so kbt in terms of joule, this is also joule, so e to the power 381, you can understand what is that value. It's huge. Okay.
Yes.
So it's 10 to the, oh no, e to the power 381. So it's showing math error. So just so now we can understand in calculator it's showing math. So it's a huge value, huge value. So compared to these value are totally negligible. That's why in general we just consider the first term. Okay. So that's why it's consider only the ground state. Now we have studied that if you consider the ground state only, then it should be QE, it should be actually what it should be 2 into e to the power minus beta
Minus beta epsilon and j.
E1, the ground state, right?
Yes.
But essentially what you have studied in the lecture, so if you remember the partition function QE is actually the G0 or G1, the ground state, right? Only the degeneracy, that
Yes.
means 2. This you have studied. So where does it go? This e to the power minus beta E1. Okay, this should be
Temperature
there.
is too low.
Temperature is too low. No, no, no. If you remember what we can do, shifting, right? Just in vibrational case, we did not relative shift,
Yes.
that we can do here also. This is the correct one. Now you can shift. Uh, let me move it. Hmm. So if you shift this to 0, now this is the state. So every state will be shifted by 13.6.
13.6.
So it, now E1 will be, the ground state is 0 electron volt. Next step, it will be goes up to, it will be at 13.6, so it will be minus
17.
10.4. No, it will be 10.2. You can add it, okay? The spacing will be the same. Overall,
Yes.
like this. So E2 will be 10.2 something, and it will goes on. So you can do this for here also. This is also relative
The last
shifting.
is plus 13.6.
The last is 0 electron volts, so it should be plus 13.6 because the energy gap will be same. I have just shifted the coordinate, you can say, nothing else. So in that case, if you do it, then QE will be 2 into to the power minus
2
beta
into
G0. So it will be 0, then it will be just 2. That's why
2.
it is G0. So now one question you might think that if you consider the original one, then the partition function is huge, right? It's huge. But if you
Yes.
consider this, then the partition function is very less too. So whether it is correct to do or not, because
Yes.
the original form this is actually huge because it is a 20 partition function. It should be huge, and it is the, if you consider the shifted energy levels, then it will be only 2, and that we generally consider this is the form. This is the QE is equal to G regency of ground state, and it is essentially the 2. But if you do in terms of this, actually considering the original energy, then it is huge. So essentially it does not matter. Why? Why it does not matter? Because if you consider any of the picture, it is clear that the in normal temperature or room temperature, or you can take the higher temperature as well, the ground state only be populated. Because the higher energy, what the partition function means, this is the population distribution, right? As long as these the other energy levels are very high enough compared to the ground state, only the ground state will be populated. Here also you can see, right? So that's why the only ground state will be populated. And if the only ground state is populated, you can consider this form as well, because when you ultimately you have to calculate the other properties. That means the function like entropy, enthalpy, internal energy, this you have to calculate. For calculating that, you have to uh, differentiate with respect to beta or other factor, temperature and anything you have to differentiate. So when only the ground state is populated, in both picture, the ground state is only populated, that will irrelevant considering the other energy level. So it can be this. It can be this, but when you differentiate it, let me just differentiate for translational case. You know the partition, yeah, sorry. You know the internal energy. What is the internal energy? That is 1 by q dq d beta, right?
Yes.
This was our internal energy. So let us calculate. So it will be here. So del q del beta at constant v. So it will be, you can write it del q del beta, and q is just consider the ground state. So it is to the power minus beta e1. It is a general form. Here there is no approximation. I am not putting the any value of e1. So it will be 2 will be there, and it will be del beta e to the power minus beta e1. So 2 by q. So what it would be? It is minus e1. Okay, is this clear?
Yes.
So okay, so it is 2 into it. So this part 2 into the minus beta e1, or I have done, no, I think it's correct. Any minus thing was there, right? Is there any minus sign here? I just don't remember.
Yes.
Okay.
Yes.
Okay, so minus, if minus is there, so let it be. Just we have to understand this. So q will be cancelled because 2 to the power beta epsilon, it is also q. So it will be just minus e1. So now you can see E1 is there, so just the ground state energy will come out. Obviously, it should be, because if all the molecules are in ground state, so average energy, what should it be? The ground state energy. If all
Yes.
molecules are populated in ground state, that's what I'm saying. Na? So now it's irrelevant. So if you consider it as Z is only 2 or anything, that it does not matter. So now you can check. Let's say if you shift the energy level, then it will be 0. Then ground state, it will be 0. Or you consider the original value, then you have to put the 13.6. So it will be, so here it was minus sign. So it will be minus 13.6 electron volt. This will be the ground state energy. This is the fact, nothing else. Okay.
Which one is more accurate?
Obviously, that this one, it should be. Because here, the ground state energy, we have just considered to calculate, you can shift the energy level, and you can do the, because when you consider the transition basically, then the energy gap will matter. It's not relevant. It's relevant. What is relevant here? The ground state is populated. The energy of ground state is depends up to you. You can consider the original value, or you can consider the shifted value. that will not affect. In both calculations, you can see that the result will be the same, the energy of the ground state. So del E average will be, you can write in general, it will be ground state energy. Just so let it may be 0, it may be minus 13.6. Why I'm saying this is irrelevant? Because when you calculate any property, let's say if you want to calculate CV, what was CV? Daily del T V.
It be a constant V.
What will be? If you put any value, it will be 0. If you put minus 13.6, then also it will be 0. If you put 0, then also it will be 0 because it's constant. So
Yes.
when the only ground state is populated, the E average may be anything, but when you calculate the properties, CV or other properties, transition properties, which is a system property, you can't calculate the internal energy, correct? You have to calculate the heat capacities or these kind of things. Then it will be obviously 0. It does not impact. That's why we consider, okay, both are correct. This is a shifting. We call this is shifting. Just we have shifted by 13.6 electron volt energy. Rest of the party. Physics is the same. Physics will not be hampered. The energy magnitude may be different. Okay. So I think it's clear. That's why I thought to discuss, because the same thing happens when you discuss the uh, vibration energy as well. You have seen that. They are also two different values. But last class I shown that you can consider the any value, the CV will be the same. The vibrational contribution to the CV, that will be the same. That does not matter. By shifting that energy level, the physics will not be changed. Okay, so this is the electronic partition function. No. So now we can discuss something about, this is very important, Gibbs paradox. Okay. So from here you will understand why the n factorial appears. The statistical thermodynamics or statistical mechanics is basically developed by Gibbs. This ensemble, the concept of ensemble was given by Gibbs as well. So now discuss. I know this is quite theoretical class today, but it's important because the discussion is not theoretical. It will be a bit calculated. So just I want to discuss. Do you have any idea about this? Do you have listened about this Gibbs paradox?
Only the name.
Okay, you have listened the name. Then it's great. It's a very famous question in interview. If you choose the statistical thermodynamics part, from where the question can be asked, then Gibbs paradox always there because it's very important. Okay, so let me. So first, you know the entropy. What was the formula for entropy from statistical
KB
thermodynamics?
ln omega.
No, that is residual entropy. Don't confuse between these two things. That is residual entropy. Residual entropy is due to the that orientation of that molecule in solid state at absolute zero temperature. That is different. Okay, these two things are very important. Just understand this. The thermodynamics is
U
basically
minus U0 by T that.
exactly that is the form, but that is due to the temperature. That is due to the distribution. Statistical thermodynamics, right? Statistics when you have statistical distribution. When there is some temperature, if there is zero temperature, everything will be flat. Just we have discussed, every population will be in zero state, and if every population is the not zero ground state, if every population is in the ground state, then the energy, internal energy will be zero, everything, entropy, everything you can consider. So that will not contribute. That's why that law, na third law, for perfectly crystalline solid, it will be zero, because for that there is no residual entropy event. Residual entropy is KBLN omega. That is different. This entropy is not residual entropy. This is thermodynamic entropy. These two entropies are different. Okay. There are
KPLNQ plus
KBLN.
average energy by T. Na?
Exactly. That is the thermodynamic entropy. There are other entropies as well. Do you know this? Except this residual entropy and this thermodynamic entropy, there are other entropies. Like, do you heard about Maxwell demon?
No.
Okay, so that Maxwell demon, that is also a paradox-like things. So that I can discuss later. In I think in the last class I will say something about it because this is very very interesting. For this Maxwell demons was a paradox. Um, you can consider up to 1970. Then it was solved by Landwehr. I think Landwehr, and he got Nobel Prize. And from when it was solved, this Maxwell demon paradox, it was solved. That information, everything you do today, that computer, binary operation, everything that that was very I think that was scientific even in terms of statistical thermodynamics, statistical mechanics. It was mathematics. I can't express the word actually. You can now write the formulas for those things. You have 0 and 1, these binary things, but when you write 0 and 1, there will be a entropy increment that you can now do in terms of formulas. So that you can solve. Okay, that when I will discuss Maxwell demon, I will say. Okay, so what was that entropy? This is thermodynamic entropy. Let me write it again. Okay, so this was E average by T plus KBLN Q, right? So this was our entropy. Okay, one thing, this formula do you have ever seen? Um, this formula,
What is the TR?
trace, trace over rho and rho.
No.
Okay, this is related to that KBLN omega. Okay, this is our residual entropy. This is our Gibbs entropy. Trace is nothing. Trace, you know the matrix?
Yes, the sum of the corner elements.
Diagonal element. That is called trace. So rho is a matrix. Rho is called density matrix. So this is very important. If you know density matrix for any quantum state or any statistical distribution, any state, you can think, because you know in quantum case there are many states. So if you know the, just like partition function, right? If you know the partition function, you can calculate the thermodynamic entropy. Similarly, if you know the density matrix of any quantum state, just using this formula, you can do it. So it's actually great. This is a mathematical formula, okay? And in mathematical formula, there was no table. That there was space over rho L and rho. So when you because this is totally mathematics, density matrix obtained in mathematics. When you just multiply it with KB, the value is actually matches with the physical entropy, physical experimental residual entropy, whatever you can have. That actually matches. That was amazing. So that's why entropy is the only thing in thermodynamics. Everything you have studied, internal energy, enthalpy, Gibbs energy, these are not the first element. You can say entropy is the only thing what you can derive from the first principle, from the math even, without having any physical idea, just from math. So that's why entropy is ultimate, you can say. And you know that entropy should be always greater than zero. This is the condition for spontaneity. Everything is guided by the entropy.
Yes.
Okay, so now just write down the formula. What now? Just you have to put the value of Q and E. Let us consider, just I am considering monoatomic gas. Monoatomic gas. So now, then what will be E average?
5/2 R.
3 by 2 kVt.
Sorry, 3/2 R.
kVt. You just consider kVt for one molecule only. Okay. For one gas molecule. If you multiply it with the Na, it will be R. This is clear. This is just a matter. And what will be this? KBln Q to the power N, right?
Yes.
I have written Q to the power N. That means we are not considering the indistinguishability. We are considering the gas molecules are distinguishable. Okay. So it is NKB ln Q. And we are considering only monoatomic gas. So it will be only Q translational. Because there is no rotational vibration, anything is not there. So it will be only Q translational. So what is the form of Q translational?
2 pi mkbt by h square whole to the power 3/2 and
2
VQ
pi m kBt by
h square whole to the power 3/2.
whole to the power 3 by 2. Or you can, in terms of v lambda, you can also write it. Correct?
V cube by lambda cube.
V cube by lambda cube, that you can also write it. So here the form is written. Just let me write it. So it is V. If you consider, I want to write in terms of energy. E. Then how you can write? You get in terms of energy. If you want to write, so how you can write it? There was a derivation. That was not done. Okay, then just let me write it. Okay, then we can think how it can be written. But the same for NKB. Okay, N will be there. This is for one molecule. This is for one molecule. If you calculate for n number of molecules, if it is Na, then it will be R. But if it is not Na, for any number of molecule, it will be multiplied by N. So it's better to write NKB. That's why N is here as well, right? So let me multiply it with just N. I think it's clear. For one molecule, it's KBT. For n molecule, it's NKBT. That's it. And if it is Avogadro number of molecule, then it will be NAKB. That means R. That's different. So it is NKB. It is written as V by H cube divided by 4 pi ME divided by 3n to the power 3 by 2. So check it whether it is correct or not. Is it correct? How you can check? Just put the value of E here, right? Just do it. Just put the value of E. What is the value of E?
N square h square by 8m
No, no,
square.
no, no, no. Already you have the value of E. This is the value of E, na? 3 by 2 NKBT. This was the value of E. Just I want to just write in terms of E, nothing else. So it is V by H cube. N and will be cancelled out. 3 will be goes away. So it will be 2 pi. Then KBT to the power 3 by 2. So I think it's correct.
The M
M is there, right? M is here also. So M is there. M is there. Thank you. Okay. And V. We are all this was Just remember, just remind me, what was the QP? V by
Lambda
lambda
cube.
cube. And lambda was root over 2 pi m
KBT by H.
kbt by h. So it was uh, V by lambda cube. It was a 2 pi or
H cube.
no. I think I have written wrong. H by 2 pi. Let me check. It should not be wrong. Let me check one second. Then it will be
Yes,
easier.
H by.
H by, right? Yes, it is actually h by root over 2 pi m kbt. So it will be h cube over 2 pi m e to the power 3 by 2. Correct? So it matches. So here you have missed a v. Here was a v. So you can write the entropy in terms of this. Is it okay?
Yes.
This form? Okay. Okay, so entropy is nkb ln v by h cube 4 pi m e divided by 3n to the power 3 by 2 plus 3 by 2 nkb. If it is na, then it will be r. Okay, so it's correct. So if this is the form of n, s, the entropy, one thing we can check right now. Just we will go step by step. This s, just now let me write it as uh, nkb. You will also check. I make some mistake, so please you can check it. So it can be written as v e by n to the power 3 by 2 plus 3 by 2 nkb ln 4 pi m divided by 3h square plus 1. Okay. Is it correct? 4 pi m.
Yes.
Yes. You can check it. It will be same. So in general, you can write it nkb ln v v e by n e by 2 plus nkb s0. Just I have renamed it, where s0 is 3 by 2. Why I did this? Because you see, this V, E, and N, these things are important. These are constant. M you know, H you know, 1, pi, everything is constant. N, KB. So this part is totally a constant part, right? So I have just removed that constant part totally. Is it clear? So it's better to consider only this
Yes.
part. So I've just removed the. So this formula is widely used because here only the relevant terms are there. These constant parts are removed. So these are all constant. Okay. So now let's say if you had a gas, okay, which has entropy S1, okay, and there is number of N is the number of molecule, volume is the V, and energy is E. Okay, just now you changed it. Just I'm changing anything you can change. Uh, so now it is now alpha times N, alpha times V, alpha times E. It may be 2n, 2v, 2e. I have changed the system mass, a system number of molecule, system volume, and the energy of the system. Everything I have changed, and let's say it is the S2. Then I have to calculate the S2. So S1 and S2, S1 should be the same like this, n kb ln e by n to the power 3 by 2 n kb S0, and S2 will be now, it will be alpha times n kb ln alpha times v, e by n, alpha will be goes away, so 3 by 2 alpha times n kb S0.
In the S0 term?
S0 term you can check, is there anything that will be changed?
No.
No. That's why I have written na, in terms of S0. That was the beauty of that equation. That will not be bothered. Whatever you have change in number, energy, it will be same. Okay. So I can write it. Uh, so now from the knowledge of our thermodynamics, you know that S is a extensive property, right? Entropy is a extensive property.
Yes.
It's if S is a extensive property, so when you change alpha times, so S1 should be also changed by alpha times. Correct? What I am
Yes.
saying. So if that is true, then S2 should be equals to alpha times S1.
Yes.
So that we have to check. Alpha times S1 obviously will be n alpha n kb ln v e by n 3 by 2 plus alpha n kb S0. So you can see S2 not equals to alpha times S1. Is it
Yes.
matching? It is not matching. Why? What? This alpha is there. Here is no alpha.
Yes.
So it's not matching. So what does it mean? It means that this equation is not correct. This equation we have obtained for the entropy, that is not correct. If that was correct, then it will be consistent with our classical or chemical thermodynamics result as well. So we need modification. So from here, while doing this, Gibbs got this idea. Gibbs was shocked. This should not be thing, right? Everything we are doing from statistical to calculate our uh, chemical thermodynamical properties. So this thing should not be there. Chemical thermodynamics property we have already checked. That are verified. So that should be consistent with the statistical thermodynamics description. So that was not matching. So that's why to just pinpoint the problem, Gibbs did a thought experiment that I want to say. That is the Gibbs paradox. And when you solve this Gibbs paradox, this problem will also be resolved. So Gibbs said that let us consider, okay, this this formula, that v into e by n to the power 3 by 2 plus n kb S0. Okay, so let's say Gibbs said that, okay, consider two cases. First case 1, we have this a setup like this. Okay, we are considering different kind mixing of case 1. In case 1, we are considering mixing of two different monoatomic gas, because this alpha formula is only valid for monoatomic gas. So you have to consider them. So let's say here is neon and here is helium, or not helium, it was considered argon. Okay, two gases are there. This is N1, V1, T1, and this is N2, V2, T2. So now he considered the mixing, just he removed the partition. So both gases will be mixed up. And now the number of molecule will be N, which is N1 plus N2. Obviously, the volume will be obviously V1 plus V2. And the temperature will be same. The temperature was same as well first. Why temperature is same? Because we are considering canonical ensemble. So the temperature should be same. So this will be NPT. Okay. So if this is the case, so now we have to consider the entropy. So first, this is the initial state. This is the final state. So for in initial state, what was the entropy? Let's say for S1, this is 1, this is 2. For S1, what will be the entropy from this formula? It will be N1 Kb. Just I'm writing from this formula. N1 Kb ln V1 E by N divided by 3 by 2 plus plus it was it is N1, so it is also N1 Kb S0. Okay, clear? Or let me write it as N neon. For argon, it will be N2 Kb ln V2 E by N2 divided by 3 by 2 plus N2 Kb S0. Okay, is it clear?
Yes.
Yes.
But these are for initial state. Now we have to calculate for final state. So final state, what would be in final state? Both gases are mixed up. So if both gases are mixed up, so now you can calculate the entropy.
It will be added up.
It will be added up. So just you can consider this as a whole gas because it does not consider whether it is neon or argon. It will be same. Both are monoatomic gas. So you can consider the same both as a monoatomic gas. That's why I'm saying both are the you can consider as monoatomic gas. So as both are the monoatomic gas, so essentially it would be S, the entropy, total entropy. It will be, let me write it for neon as well. Neon final. It will be N1 plus N2. No, not N1 plus N2. It will be N1. Number of molecule will be N1 Kb ln. The volume changes. Volume is now V, which is V1 plus V2. It will be E by N1 divided by 3 by 2 plus N1 KBS 0. Okay. What is for argon? It is N2 Kb ln. Just I'm writing same thing. We will just N2. V will be the same for both gases now. So now if you add total entropy final will be N1 plus N2, which is N Kb to add it. So it will be just let me write it N Kb ln. No, one minute, because here is N1, here is N2, so you can't add like this because both N are different. Okay, that you can do. That you can do. Okay. This part you can ignore actually. This E by acha acha. Okay. One thing I just this is E, right? E for energy. This E energy and E by N. So E by N will not be changed. This you have to understand, right? E by N will be same. Why? This you have to understand. This is E by N1 and this is also E by N1. So this E by N1 is not changing and both it is actually E1 by N1, it is E2 by N2. Let me write it. Now it will be clear. So this E1 by N1 should be equals to E2 by N2. Okay. Why I am saying this? This is very trivial question. Why this E1 by N1 should be equals to E2 by N2? because the temperature are same. It's canonical ensemble. So there was restriction, right?
Yes.
So both temperature are same. So when you multiply, consider the energy by number of molecules, so it essentially consider the temperature. That is same. So that
Yes.
means the U1 by 1, that is, so we can ignore that. That's why U1 by N2, this part was not considered here in the book. Okay. But if you do uh, by calculation, so this will be there. So in general, these are the same. So you can write it KB, ln, V, any of these two. Let's say I'm writing U1 by 8. Both are same. And it is N KB S0. So it is S final. Okay. And what was the S initial total S? Then you have to add up these two things. So let me do it. If you add these two things, what will it? It will be S initial. It will be N1 KB ln V U1 by N1 3 by 2 plus N2 KB ln V N E2 by N2. It was V1, it was V2, just 3 by 2, and N1 KBS 0 plus N2 KBS 0. Just I have added up these two things. Just check it. The same thing I have just added up. So here you can see it is N1 KB ln V1 plus N2 KB ln V2 plus N KB ln V1 by N1 to the power 3 by 2 plus N KBS 0. Just check it whether it is correct or wrong.
The E1 by N1 is neglected.
No, both have E1 by N1. These are the same, right? So I can replace it. E2 by N2 can be also like E1 by N1. Just I have taken out this. Then it will
Okay.
what will N1 plus N2, that is N. Okay. So I can write it. This also I can write it. N KB ln V plus N KB ln E1 by N1 to the power 3 by 2 plus N KB S0. So just you consider that now del S change in entropy. So it should be S final minus S initial. So you check these parts are the same. So only change will be N KB ln V N KB ln V minus N1 KB ln V1 minus plus N2 KB ln V2. So what you can write it? You can write it N1 KB ln V plus N2 KB ln V minus N1 KB ln V1 plus N2 KB ln V2. So it will be N1 KB ln V by V1 plus N2 KB ln V by V2. So this is our del S, change in the entropy. This change is entropy of mixing. Should be because it is due to the mixing of entropy. And V is greater than V1. Obviously, V is V1 plus V2. So V is greater than V1 and V is greater than V2 also. So del S mixing should be greater than 0. Okay, in thermodynamics, also del S mixing is greater than 0, right? For spontaneous mixing.
Yes.
So it is consistent with the thermodynamics. There is no wrong. Okay, there is no wrong. So now you can understand why the del S mixing is greater than 0 is entropy is mixing. Why this is happening? Because it's clear. You are removing the partition, right? You are removing the partition. Now, for both of the gases, for neon, if you consider for neon, it was n number of molecules. For n number of molecules, there was V1 amount of volume. to be roam around. When you removing the partition, number of molecule is fixed, N1, but now the volume increased to the V. That's why you can see here it is just N1 KBln V by V1. That this is VX. That previously the volume was V1. After removing the partition, the accessible volume becomes V. So this amount of entropy will be increased because entropy is randomness because he is now enjoying large amount of volume. So from there, this del S mixing is there. So you can check uh, anywhere. Do you have considered the molecules are same or different? Whether it is if it is instead of neon and argon, if it was neon and neon, then also the overall derivation, the discussion will be same. Okay, is it clear? There is nothing.
N1 and N2 are same.
Everything will be same. No, I'm saying that while discussing this, we have considered two monoatomic gas. Never we have considered this is neon or this is argon. If I'm saying if this is the both are neon, then anything will be changed or not? Let's say both
That
are
will be
neon.
same.
Every calculation will be same. Nothing we have done with regarding to that characteristics of that gas. So everything will be same. So this is the general result we obtain for uh, different gas or the same gas. Any monoatomic gas. If two monoatomic gas mixes, then the entropy will be increased. But you know from our classical thermodynamics, when two different gases are mixed up, from classical thermodynamics, you know when two different gases are mixed up, then del S mixing is greater than zero. But when the same gas mixes, then del S mixing is zero, right?
Yes.
That is not consistent here. That is the Gibbs paradox. Gibbs point out this. Here there is nothing with the same or monatomic gas, same or different gas. So according to our calculation, if the same gases mixes, then also the entropy should be increased. If you think there were two same gas, both are neon, you remove the partition, so both gases mixed up, entropy should not increase because both before also for neon this was N1 plus N2 number of molecules were enjoying V1 plus V2 number of amount of volume. If you remove the partition, nothing has changed. So entropy should not be increased. So that is Gibbs paradox. So that should be resolved. So now you can guess what is the way out. What is the problem? What is the wrong in this calculation? There must be something wrong. That's why you are getting the wrong result. For different gas, it's okay, but for same gas, it is giving the wrong result. Why? This result is correct for the different gas.
That's V type volume.
No, volume is increased. What is the difference between a different gas and same gas? That should we have understand now. In different gas and same gas must be some differentiating factor, which will lead to different result. That we have not considered. That's why we are getting the same result for different gas or same gas.
Yes.
What is that? We have considered the molecules are distinguishable.
Uh, yeah.
That's why we have written capital Q equals to Q to the power n. If you remember, that we have written
Yes.
and we have written here. Q Q is written as Q to the power n by n factorial. Sorry, Q to the power n that we have written, but that means we have considered the distinguishable. But in case of different gas, it's okay. Different gas molecule can be considered as distinguishable. For same gas, it's not totally correct, but it's okay. For different gas, molecules are up to some extent distinguishable. But for same gas, how can molecules can be distinguishable? It should not be distinguishable. Okay. For same gas, you have to consider that this indistinguishability factor. Okay. So that means our entropy will be here. Here we have considered this. This part will be same. So now just we have to change it. What will be? What change will be there? Just we have to incorporate the in factorial part. Here two approaches can be there. First we can consider the n factorial, then we can show the consistency. Otherwise, we can guess that there must be n factorial. What um, treatment do you like to do? I do according to that. Okay, let us consider n factorial. That will be straightforward. Okay, then it was our normal definition. It is the same 3 by 2 n kb. It will be changed. It will be kb ln q to the power n by n factorial. Just check. N factorial is n ln n minus n from Starling approximation.
Last KBN.
Hmm. So it will be 5 by 2 n kb plus minus n kb ln n. Okay. So this is our now form of entropy. But we have to reorganize these things. This n kb ln q, if you go here, this we have just changed in terms of energy. This n kb ln q, this part I have written in terms of this. Just I will copy paste it. Okay. N kb ln this part q will be only the translation now because we are considering the monoatomic. So it will be just post it. Okay. It's correct. One more thing will be there, that is what you can write it. This is q by n actually.
Yes.
So just you have to divide it by one more n. So we can consider this form. So now we can write it as n kb ln. Just check. It will be d by n e by n to the power 3 by 2 plus, just we doing the similar stuff. Here it will be, sorry, let me write it. It will be n kb 3 by 2 n kb. No, n kb is 0. Okay, this just same thing. S0 will be 5 by 2 plus 3 by 2 ln 4 pi m by 3a square. Okay, so now just you can put it and you can get the same thing. Same treatment I am doing. There also I have just separated the constant part in the S0. The S0 has only the constant part. Previously it was, if you remember, previously it was 3 by 2 ln something plus 1. That means here it was also 3 by 2. Yes, yeah. Yes. This means C by 2 ln this 4 pi m square plus, or you can write it like this. Okay. This is only changed. This is become 5 by 2. Otherwise, this part is same. So this is our now formula. So this just you can see the changes is only here 5 by 2 appears, that is constant, so that is not important. The important part is this v, instead of v we have now v by n. Previously we had v only. So this is our new form, and this is the form for second tetrad equation. If you remember, this was the uh, in terms of energy. This is the in terms of energy. This is second tetrad equation. This formula you can also consider as second equation. Okay. Now you check everything is done now. If you consider this formula, then just similar treatment we have to do n1 n2, that we have done. So do it. So first, before mixing, so again we are considering the mixing. It was n1 v1 at t, it was n2 v2 at t. That after removing the partition, it becomes n v. Okay, so do it. So what will be s neon here, or s1 I'm writing, maybe neon anything initial. You have to consider this equation. So it is n1 kb ln v1 by n1. E by n will be same for both cases. So E by, I'm not writing 1 or 2, it is same. So n divided by 3 by 2 plus n1 kb s0. For s2 initial, it will be n2 kb ln v1 by n1 E by n to the power 3 by 2 plus n2 kb s0. Correct? So total S initial will be, it would be V2. It would be N2. Just correct me if it is wrong. Then it will be messed up totally. So it is NKV ln V1 by N1 plus N2 kb ln V2 by N2 plus N kb ln E by N to the power 3 by 2 plus N kb S0. So this is S initial. Just add it. And what would be now S final? So S final for S final for 1. So it would be now capital N1 KB ln, instead of V1 it will be V by N1 E by N to the power 3 by 2 plus N to the S0. N1 to the S0. Okay. And S2 final, not initial. It would be N2 KB ln V by N2 E by N 3 by 2 N2 KBL0. Now we add it, so S final will be N KB N1 KB ln 1 3 right this side V by N1 plus N2 KB ln V by N2 plus N KB ln E by N to the power 3 by 2 plus N KB S0. So this is S final. So del S will be S final minus S initial. If you check, this part is same, N kb part, and this part will be same. This is different. So it is just we have to divide subtract from this part to that. That you check only difference is only there. This is V and this is V1. Same thing. Only here N1 is also there. In previous case there was no N1, but here N1 is there also. So it is N1 KB ln V1 by N1 minus N1 KB ln V1. Sorry, V by N1 and V1 by N1. This is plus N2 KB ln V by N2 minus N2 KB ln V2 by N2. So it is N1 KB ln V by V1. The same formula we obtain N2 KB ln V by V2. Just check the same formula we have obtained. Okay. Okay. But okay. So initial is correct, but in final it will be sorry. N will be there. Total for total number of molecules that we have to also incorporate. So if you consider that, so let me consider that also. That is one thing. Okay, so you can write it like this, S final. This is correct. S final. How you can write it if you consider total gas? So this would be N1 KB N1 ln V by N. What I am doing, just understand this for this case. Here there is no difference. Okay. First, okay, let me write. Just it will be this. Okay. So this is zero, right? This is same formula you have obtained for different gases. It's okay, but if you consider the same gas, then it's different. What I'm saying is understandable. Let me say it again. This formula you obtained, N this is del S mixing, and if you check the previous formula that we have obtained with our previous equation, that was also same. This formula, this is okay. That matches, totally matches. It's totally matched. But this formula in previous case, while doing the derivation, we have considered nothing about the gas. That may be same, but this is true for only different gas. Different gas. But if the gas is the same gas is there right now, this derivation is for different gas. In previous case, what was the things? That was independent of the gas. If you consider the same gas, the overall treatment will be the same. So nothing was changed. But here, if you consider the same gas, now the treatment will be different. That is important here. If you consider them the same gas, if you consider same gas, now what will be difference? That is important. For same gas, it was problematic. For different gas, we have already have the right result. The entropy of mixing was greater than zero. Here is also the same thing. The S mixing is here also greater than zero. But for same gas, it should be zero. That was missing in the last part. That we have to do. That is the difference. Okay. So what I am saying, is it clear?
How it will be 0 for
That
same gas?
that I will show. That I will show. It should be zero from our knowledge of classical thermodynamics. It should be zero, right? That I will show how it will be zero. Okay. So now consider the same gas. Let's say both animal. Okay, so this S initial will be the same. S initial will not be changed. Though also I maybe write it. S initial, what will be the S initial? S1 initial should be N1 KB ln V1 by N1 E by N 3 by 2 plus N1 KB S0. S2 initial, although here there is both are same, so N1 and this 1 2 is denoting the number. V2 by N2 E by N 3 by 2 plus N2 KB S0. So why am not writing E1 N1 by E2 N2? Because it's the same thing. E1 by N1 equals to E2 by N2. So it will be cancelled out. That's why I'm not cancelled out. It will be common, take common. So I'm not writing. So S1 Si initial entropy will be N1 KB ln V1 by N1. Now you have to remember we are doing for the same gas. This part is same, and here it will be capital N KB ln E by N 3 by 2 plus N KB S0. What will be after mixing? So now S final. Now you see in case of S final, this case, this is final case, you can't do S final 1, S final 2. Here you did this thing, S final 1, S final 2. Means for neon gas and for argon gas. One is for neon gas and two was for argon gas. This you did. But here you can't do it because both are the same gas right now. So you have to do only the S final. That is only S neon final. So now do it. It will be N. Just you have to write the now this is all are the same molecule now. So if all are the same molecule, so it should be N KB ln V by N because you are considering all are the same molecule. E by N 3 by 2 plus N KB S0. This is the, so you write it, so it will be N KB ln V by N plus N KB ln E by N to the power 3 by 2 plus N KB S0. So what will be the del S of mixing? I have to subtract this. So del S of mixing will be S final minus S of initial. So this part are the same part, so it will be cancelled out. So we will have N KB ln V by N minus N1 KB ln V1 by N1 minus N2 KB ln V2 by N2. Okay. So what can we write? N1 N is N1 plus N2 ln V by N minus N1 KB ln V1 by N1 minus N2 KB ln V2 by N2. So it is N1, if you take common, then it will be ln V by N into N1 by V1. Okay, because there is a minus sign, plus N2 ln V by N N2 by V2. So it is N1 ln V is eventually V1 by V2 by V1. It is N1 by N1 plus N2. Here also V1 plus V2 by V2, N2 by N1 plus N2. Okay. So now, from here what you can write from this mixing, both are neon gas. So check whether we can write it or not. V1 by N1 equals to V2 by N2 equals to V1 plus V2 by N1 plus N2.
Yes.
This you can write, because if you write this from mathematics, you can write this directly. These
Yes.
things you can write, so from there it is evident. So if you do it, so now V1 plus V2 divided by N1 plus N2 equals to V1 by N1 plus V2 by N2. And this is V by N. So if you do it, so you check, it will be 1, it will be 1, both will be 1. So it will be N1 ln 1 plus N2 ln 1. So it will be 0. Okay, clear?
Okay.
Just we have to insert the N1. In previous formula, there was no N1, right? So we obtained just V by V1 thing, same formula. N1 was not there, N was cancelled out. Both was same because N was not there, so it was just V by V1. Here this N1 and N is there. So that's why V equals to V1 is not correct. V1 by N1, V1 by N1 equals to V by N. That is correct. So just we have to consider that N. That gives us the correct result, totally correct result. So this is the solve of the resolving Gibbs paradox. Hence, we have to consider the indistinguishability factor, and the correct formula for entropy is this, not the previous one. This is the correct formula of entropy. Obviously, considering only the monoatomic gas. 3 by 2 ln 4 pi n 2h square. So this is for now that first part what we have did in first, the wrong result we obtained, if you remember here, S2 is not equals to alpha S1. That also we can now check using this formula whether that is solved or not. What is that problem, that it was S1 N1 V1 and P or E1, E1 2, we were changing to this alpha N1, alpha V1, alpha E1. That is S2. So that should match. S2 should be equals to alpha times S1. That was not matching the last case. Let's check. Here S1 will be N1 KB ln V1 by N1, E1 by N1 to the power 3 by 2. This will be N1 KB S0. What will be S2? Alpha N1 KB ln alpha V1 by alpha N1. So it will be V1 by N1. Alpha E1 by alpha N1. So it will be E1 by N1. 3 by 2 plus alpha N1 KBS0. So it is alpha times S1. So it matches. Okay. So anybody should guess, if you look at this part from here, it's this alpha was there only, right? So it is clear that just if you include the instead of V, if you include V by N, then alpha will be goes away. So it's clear because we are just changing everything, alpha times N, alpha times V, alpha times C. So E and N is considered, V is considered. So if you just divide it by N, then obviously everything would be consistent. From there you can guess that, and at last you see that is the correct formula. So this is the Gibbs paradox. So I think now additivity problem is also done. That is resolved by solving the Gibbs paradox. Okay, so probably today I can start the grand canonical example, but if you have any other doubt, you can ask me. Okay, from this part also, if you have any doubt, you can ask. This is quite uh, extensive part. Okay. If you have doubt, you can ask.
What is the actual definition for entropy?
Actual definition for entropy in terms of what? From statistical viewpoint or quantum viewpoint or thermodynamic viewpoint, that is important.
Statistical and quantum?
Statistical and quantum, if you say, let me write it, okay, KBL and omega, right? This entropy is residual entropy. That means you are considering a perfectly crystalline solid at equals to 0 Kelvin. For that cases, if you have any distribution, orientational distribution, orientational randomness, that will contribute to entropy. Entropy is randomness. By any means, it should be considered a randomness that will be impactful in entropy. Plus, you have to consider any randomness. It may be due to orientation, due to its translational, due to its vibrational, anything. So it's residual entropy. So
In
when
YouTube, I found that it's not just randomness. So I'm asking it.
so what else? It's only randomness. In YouTube, what you have find, I am explaining. He was saying about probably information entropy, probably this for residual entropy. This you can think a difference from randomness. It's not a our physical randomness. That's the molecule is moving, not like that. When you just imagine the picture of residual entropy, carbon monoxide, that was not moving. Molecules are fixed. That is crystalline solid. But why I'm saying the randomness term is relevant because the orientation is not fixed. Orientation can be random there. There are two probable randomness in terms of orientation. That's why the randomness happens. In information also, there is randomness in information. That's why that in entropy, when you study the same formula for information entropy, this is same formula is for information entropy as well. I was saying na, that for any binary logic, it may be 0 or 1, right? You know. So if there is only 0 or 1, two probability, so A should be KBln2. That is a informational entropy. That is very important when you're doing any informational things. This computer science, in computer science, this informational entropy is very important. Okay, so this is KBln2. There is also a randomness, but these are the uh, randomness. This randomness not due to the physical movement. That is not. But if you consider thermodynamic entropy, that is what we have discussed today. From thermodynamical partition function, you know that is E by T plus KBln Q. Okay, but that is in terms of partition function. You can do in terms of given state, that is KB trace over rho ln rho. That is more general form. That is the finest definition of entropy. Okay,
What
KB
is the row?
trace. Rho is the density matrix. Rho is the density matrix.
Could you please
How can I find it?
explain what?
What is the density matrix? Density matrix is written like this: sum over n. This is the density matrix. Means you are considering the quantum mechanical particle. For quantum mechanical particle, each state is guided by the wave function psi, right? Okay. There are several of
Okay.
eigenstates. Several of eigenstates are there. So these eigenstates, let's say it is psi 1, it is psi 2, like this. So in general, I can write it psi n. For any state, you know these things. Let's consider the ground state. So it is psi 1, psi 1. This is the inner product, right? This is the inner product,
Yes.
and this will give us a number. This is a number, but this is not a number. This is not inner product. This is an operator. This is an operator. When you operate it on something, it will give us result. Let's say if you operate this operator up to any function you can operate. Let's say if you are operating in psi, any psi 2. So then it is a psi 1 psi 2. It's eventually delta 1 to Kronecker delta will be there. So you can write it as psi 2 like this. So it is a operator, just like our Hamilton, just like you know this our Hamiltonian operator, like these things. You can write it. You can consider this is operator, and you know the completeness property, right? Okay, that
Yes.
is not important. Okay, here this rho is written as uh, in any state for any psi n, n will be changing. So sum over n psi n. And if there is only one state, then rho will be just this. If only one state is there, that is the size. So when you take uh, okay, so this is now you have this is density matrix, and you have to just take over rho ln rho ln, and you have to take the trace. So by which you can do for if you want to know density matrix, then I will discuss in the next class, because for that you need a something basic thing you have to know. Then you can. It's not very difficult. This density matrix approach is very easy. I would say it's not difficult. Just you have to understand the density matrix. You have to form the density matrix, and you can do everything. And this is the basic definition of density matrix. Okay. Okay, it is actually trace over rho, not rho. Rho is sign. This is rho. Trace over rho. Because you know, when you have to take trace, you have to sum over all diagonal element, right?
Yes.
Trace, you know, that I'm writing. Okay, this is a matrix A. It will be one. It's a 3 by 3 matrix. If it is, then what will be trace over A? It is sum over A.
A11 plus A22 plus
A.
A33. Yes.
Yes. So similarly, that thing. So trace over rho will be sum over n rho nn, and rho nn is this. I'm not if it you can do the suffix. If it is rho n m, then obviously it will be psi n psi m. These are off diagonal term of that matrix. Okay. So rho is
Okay.
the matrix. Rho is not the matrix elements. Rho is the matrix, just like this. Rho 1 1, rho 2 2, rho 3 3 in this way. These are the matrix, and these are the matrix element. Okay, you know the Hamiltonian matrix. Hamiltonian matrix is formed by the Hamiltonian element, that H11, H22, like these things. So this is the matrix. Okay, clear? Not I.
Okay.
Not clear, but and you can check. You know that for completeness property, you know that sum over psi 1 is 1, right? So for if only
Yes.
one state is there, so trace over rho should be 1. That called pure state. Okay, that I will say in last class. I had thought to say that Maxwell lemon, and you are saying the density matrix. I will also discuss that. Okay, little bit.
Okay.
Okay. Okay. So if you have any other question, you can ask. Otherwise, I will stop.
So I've got one question that
Yes.
regarding this zero and one state. You talk about entropy associated with
Uh-huh,
zero
uh-huh.
and one state.
Binary logic.
Yes. Yeah, so I'm very much curious about which one is much more stable, means ordered, zero or one.
No, no, no. Here is not the ordering is there. You have two options, right? So when you are choosing one option among these two,
Mhm.
okay, 0 and 1, among these 0 and 1, let's say you are choosing 0 or 1. For that, entropy is increasing, some amount of entropy. Okay, that is KBLN2. When I will discuss the Maxwell lemon, it will be clear. Maxwell lemon is also a paradox. Okay, that was saying proposed by Maxwell, and that was solved by including this informational entropy.
Okay, means with every energy, every change in the state, zero and one, the entropy will go on increasing. That's what you want to say.
No, no, no. It is not states. It's not like energy states. Energy increasing, not like there is two options. If you have only two options and you have memorized, let's say you have memorized it was 0, then it may be 0 or 1, so you are choosing between 0 and 1 or anything. So that memory, that information actually captures some amount of energy. That is KVLNP.
Okay.
If there is three option, let's say 0, 1, 2, then it will be KVLN3, like this.
Okay.
So it will be very clear when you, because it is a resolve of the Maxwell demon. So first you have to understand the Maxwell demon, then it will be very easy to answer.
Okay.
Okay, so let me now stop sharing. There will be another question. Okay,
So thank you.
okay, we'll again meet in the next Sunday at 4 p.m. Okay. In
Thank
next class, we will discuss the grand canonical ensemble. See you.
you.
Okay.
Okay, thank you.